Our next presenter is Grace Thaggard from Chemistry and Biochemistry. Let's welcome Grace.
Right now, as we speak, there are over 170,000 terawatts of energy coming from the sun and hurtling toward Earth's surface. To put that into perspective, that means that in a single hour of sun exposure, we can receive more energy than the entire human population uses in 1 year. So why aren't we all using sunlight to power our cars or to drive, charge our computers? And the challenge is that although there's plenty of energy to go around, we're really not very good at harvesting it and then storing it to be used later. The good news is that plants have already shown us that it's very possible through their natural photosynthesis. But there are a couple of things that plants do that we struggle with. So if we were to be able to peel back the layers of a leaf, one of the things we might be able to see is something called thylakoid stacks. Now these stacks are groups of molecules that harvest or absorb light, like chlorophyll. And within these stacks, all of these light-absorbing molecules are precisely oriented next to each other to absorb the energy and then hand it off to the next one, just like a molecular assembly line. So there are two things at play here. The molecules are organized, number one. Number two, they pass off the energy from one to the next in a directional manner. In other words, it's controlled. So in my research, I tried to create an artificial leaf in a synthetic material called a metal-organic framework, or a MOF. Right here, I'm showing you a real picture of a MOF, and as you can see, it's crystals. This crystalline nature is really important because that means that we can know and predict and control exactly where all of our molecules are. So in this schematic that I'm showing you, all of these gray triangles, those are the metal parts of our metal-organic framework. And we can put organic molecules between those metals. We know where the metals are, so we can take any organic molecule that harvests or absorbs light and place them inside of our MOF, and we know exactly where they are. And we can control their orientation to mimic the organization of a leaf. But I didn't say that we only need to organize, right? We also need to direct or control the energy. So what we do is we take photochromic molecules. Now a photochromic molecule, like this one I'm showing you here, means that it changes between multiple states depending on the light that it's exposed to. So if we start here, this molecule, which we can anchor between the metal nodes of our MOF, will absorb UV light. So that's our energy harvester. But as soon as it absorbs that UV light, it switches to this state here. And this state is strongly emissive, meaning it can donate that energy to the next molecule in its assembly line. So by integrating photochromic molecules into MOFs, we can create sustainable materials that behave like a leaf for the next generation of renewable